All right, so now let's look at how to make the turn the SI model into MATLAB code and plot that. So let me hide my picture, and I already have up the model that we had previously worked on, the I model, the model that assumed that there was an infinite supply of susceptible people, and that the only thing that will determine the rate of growth of infections is the number of infected people. So we can see a nice exponential growth curve over on the left, and we have our code here. So you should pull up your code for the I model because we're just going to alter it in order to make the SI model. And we're going to keep doing that as we make the model go all the way to the SEIR model. We'll add one letter at a time and keep updating our code. Here you have your code. If you can't use two computers to see the video and code along, I will attach this code to the document that you'll be doing your homework in on the last page, and you'll be able to type it in later, so you can just pay close attention. So what is the first thing we need to do here as we approach this? Well, first we better save this as a different name. So always, before you begin tinkering with a file, if you have a perfectly good file, you don't want to alter it until you've renamed it. Otherwise, you're changing the old file. So we need to change this to the SI model and save it. Otherwise, we will mess up the I model that we had. So I should change the SI model. Oh, and I probably, let's change the description. This model for the spread of disease is only dependent, that is no longer true. Is dependent upon the state variables S and I. Okay, now I might want to shorten this up, given I'm going to make my coding window a little bit bigger, but given my font size, let me just move this down and tack this onto the end. Okay, and let me give myself credit as the author. We'll Kurt, not Gert, but Kurt. I'll be teaching typing class. Owen, and then the date is 3/28/2020. All right, so here we go. You don't need to write. Well, you could write that I'm the author and that you are the editor, if you wish. Don't say that you are the author, because that would be untrue. Put that on one line though, so you keep the line numbers the same. Okay, so down here in line 7, this is the next thing we need to change. Remember, we, in order to make the derivation of our model easier, we started working with percentages infected. So let's assume that our initial infection is going to be a very low percentage of the population, 0.1%. That's actually a lot larger than the what we had in New Jersey. So this shouldn't be the initial number, but the initial percentage or proportion. Infected. Okay, so it's 0.001 out of 1. Okay, so it's the initial proportion infected. Okay, then we can keep the A value the same. We'll keep working with the infection. I think it's nice to count in weeks because days happen too quickly. We'll keep 10 weeks, keep DT the same. Imax will hold it for now. We may see when we go to graph that we'll want to change that. All right. Now, in this model, we don't need, even though we're going to use S, we don't need to put S0 here because I0 determines S0. So when we get down to the calculation section, we'll be adding S. All right, let's see, do we need any other parameters? I believe that is it. So let us keep on going down. We're going to initialize our time vectors as before. So you can see there are very few changes we're going to need to make. we're going to have 0 infection at first. And then here in line 18, you can see we made sure that we have a little bit of an infected population by the end. Oh, I did think of one thing in the parameters that we could change. The infected, the maximum is 100% of the population. We know that. So let's top our graph off at 1.2, just to give us a little buffer at the top. We will not graph above maybe 1.1 actually would work quite nicely. So that will give us a top to our graph. So we know what that is since we're dealing with it as a proportion, not as an absolute number. Okay, now moving along. So we have our time vector created, we have our infection vector zeroed out, and then we put in the initial value for the first time step. Now we're ready to do calculations. We can keep the same loop. We just now have the I times S model. So what we might want to do here is say that for each step, let's add an S of IT. S of IT should equal 1 minus I of IT. The number of people who are susceptible, oh, I should probably use capital S since I'm using capital I. The number of people who are susceptible, or the proportion who are susceptible, is equal to 1 minus the proportion who have already been infected. So we can use that in our code, and then we can keep this formula nice and simple. Now you'll notice the first time through the loop, I1 has been defined, so S1 can be assigned a value the first time through the loop. And then we can simply turn this into A times I times S for each time step. Okay, so S of IT can exist because I of IT does exist. And then we can turn around and use S of IT to determine what the DI is this time. Okay, so remember in the last model, it was simply A times I. Now it's A times I times S. And that should update the model. So now I have orange over here in the editing box. Ah, yes, I never initialized S. So I have an I vector. I need to have an S vector, which is also zeroed. And now you can see up in the upper right-hand corner, I have a green box in the edit window, which means that syntactically everything is good. I've defined S instead of letting it grow inside ahead of time, instead of just making it grow as the loop cycles. So there are zeros in all of the S values now, and then as we go through the loop, the S values will be filled in along with the I values. Let's see what happens if we plot it now. Okay, so we'll alter the plots, but let's just start by running it and see what happens as we plot. Wow, it even worked on the first time. That's great. Look at that. It's a logistic growth curve. We have a logistic growth curve here. We start out with some exponential growth. We have a point of inflection right here. Oh, and look at that. It's right at 0.5 in terms of the number of infected people. So right at 0.5, we have for the number infected, right? We have a bend in our curve, all right? And we have, so we now have a logistic growth curve for our population. That was very little that we had to change. Now let's see, do we need to alter anything? I think the one thing we might want to do is, now that we have an S curve that's not just an infinite population, we might also want to be able to plot an S curve. So it looks like we're going to have two different things we want to plot. The number of infections. Oh, actually, I should say not number, but proportion. and proportion. We don't build up to having one person infected. We have 100% of the population being infected. So let me do that again. There we go. So this is all about proportions of people infected in the population. All right, so we probably want to also be able to plot a S-curve. All right, so let's create something called plot choice. We've seen that many times. And we're going to initially set it equal to 1. And let me put a space in there, and let me write a comment after that. We're going to build this up. Since this is the SEIR model that we're building up to, we're going to say that 1 is equal to S, and 2 is equal to I. Just make that more compact because we're going to add a couple more. 2 will be I. All right. So right now we have everything set up to run it on for plot choice 2, but we need to go ahead and redo it for S. You know what we can even make? Let's do this. Let's also make a case 3 for now, which will do all of them. Okay, so let's make some cases down here for the plots. So we're going to switch on plot choice. What we have here is case 2. We need to build in a case 1. And we're going to also need to build in a case 3. And then we'll have an end to our switch plot case, our switch case statement, and let's indent it. So I'm using Control I. You could use the indentation up here, but knowing Control I is nice. Okay, so if we run this on case 2, let's make sure we didn't mess anything up. So if I put this on plot choice 2, it should give us exactly the things we had before. So now we need to create plot choice for 1. Okay, so we need to create case 1. And as we often do, it's nice to just cut and paste. So let me just copy all of that. You don't have to start from scratch. Let's paste it just with, bring my plot back. Okay, so the only difference here, let's start at the top. We are going to want to plot the number of susceptible people first. So we change the, whoops, the T is not being changed. We want to change the I to an S. All right. We will want to go from 0 to I max will work. Okay, that it turns out that that's the whole population. So we're simply going from 0 to 1.1. We want the grid to be on grid minor. The X label is the same, but it's not for the Y label, it's not the proportion infected, it's the proportion that are susceptible. Okay, the title then should be the proportion of susceptible versus time. Okay, and since it's a title, I'll probably make that capital look nicer. So let's see what happens if we run case 1. Look at that, the susceptible population, it started as the whole population, but as people become infected, it drops down the other way. So we have a nice graph for that. Now, one thing that could be good is to start getting some different colors, right? So let's say, what's a good healthy color? We'll start with blue for susceptible. Maybe we shouldn't, they're not totally healthy, they're vulnerable right now. So we'll start with blue for the healthy ones. But let's change our infected ones to red. So let's come down to case 2 for infected. Instead of a blue line, let's plot a red line for case 2. So we'll be able to see when we switch back to plot choice 2. It's now red. So those infections, so what I did in the code, in case 2, line 41, I had changed the color in the plot from a B to an R. So we have a red curve for the infected population. Right? Now, case 3, we want to put these two things together. Now, case 3 will look a lot like case 2, but we're going to have a double plot statement. So let's just copy everything that's in case 2. And for case 3, we're going to want to plot that. The line width we'll put at the end. Dot, dot, dot. Let's go down a line. We now want to do also, at the same time, we want to plot T versus S. And once again, that was in blue. So let's put it in as a solid blue line. And we'll use a line width of 2 for both of those. All right. Now, we probably want to set up a legend. Okay. Let's say proportion for the Y label. Let's do proportions of S and I. And in the title, we'll have proportions of S and I versus time. And let's run this on case 3. So notice the changes, we're going to be doing both things. So the biggest change is what's happening up in the plot statement. It's a plot statement with 2 plots in it, so that we can avoid using hold on and hold off if we do it all in one plot statement. And we should be able to now run this. Plot choice 3. And now there it goes. We can see both graphs at the same time. So we start with a very low proportion that are infected. That proportion grows over time. By 10 weeks, everyone's infected. So the susceptible population has dropped to 0 because they've all switched over to the infected population. All right, now let's play around with this a little bit. The A value, right? Remember, that was the thing that drove the rate of the infection. Let's bring it down slowly. So it's 1.25. Let's bring it down to 1.1 and see what happens. You can see that it took a little longer for the population to shift over, and we can change it down to 1.0. Once again, that's making the time it takes. I'll keep lowering it and running it. Let me make the graph bigger. That'll look nicer now that we have the code in. We don't really need to see the command window for now. So there's 0.9. If I go down to 0.8, we can see it extending over more and more time, okay? And a big part of an epidemic is buying time until you can get a cure or a vaccine for the epidemic. So if we can make our A values smaller, it buys us time where the rate of the infected population takes longer and longer to grow. So we have people being susceptible still, but it's taking longer for them to become infected, and at any given time, fewer of them are infected. So it's giving us time to adjust and to meet the medical demands. Now, remember, if I wanted to find a specific value, let's say I wanted to find the last susceptible value, I could just say, this is actually the minimum susceptible value, min S. I type that in. Oh, it gives me 0. That's not the one I wanted because it never added on the last one. Let's change our code so that won't happen. After the calculation loop, we simply didn't calculate the last S. You can see how this blue line drops straight down. So let's just say that S of We've gone to nt minus 1. So s of nt, that will be the last one, should equal 1 minus I of nt. That will just give us a last susceptible value. You can see how that changed it. So now if I take the minimum of s, I can see that it's 0.4815, and the maximum of I will be the last I value. And when you put those two things together, they do in fact add up to 1. That's the way we made it model. And so that's how you can pull off values in order to be able to answer questions in the homework. All right, so I think we have a completely working model now that has S and I in it. You could see the heart of the matter was line 26. Let me just highlight that. We needed to change the model to have A times I times S in it. Everything else we changed were just minor changes. And we also changed the idea that we're working with proportions now instead of absolute numbers. So that makes the model work for any population size, and it makes the math a lot easier to work with. Okay, so that ends the coding that we need to do. Use this code to answer some of the homework questions.